Okay guys, so welcome to our first lesson on torque and equilibrium. So let's just get right into it. Some of you have a kind of an understanding of torque if you're into cars, but I don't know actually if you really understand what torque is. So here we go. Torque. Torque is leverage. Torque is the ability to spin things effectively. It's the rotational equivalent of a force, and as such, we require force to cause a rotation, which is why I'm combining our unit on forces with these ideas of torque here. They flow very nicely one into the other. So torque is leverage, the rotational equivalent of a force, and if a net torque acts on an object, the object will spin. I want to take a look at the formula sheet here for a second. It's organized relatively nicely. These guys here were the vector, or are the vector dynamics equations on your formula sheet. You were introduced to them in grade 11, which is why I didn't really highlight them. You shouldn't need a formula sheet for these three, but here they are. Torque has one equation associated with it on the formula sheet. It's this guy right down here. This little guy here is torque. It is not the true torque equation. The true torque equation is a cross product that you'll look at when you hit true multiplication of vectors in university. But to introduce to you the concept of torques, this is the formula we're going to deal with this year. So here we go. Here we go. Where am I? So let's consider what happens when you push on a door. The door is going to open, and it is amplified. The speed at which the door is open, or the opening of the door, is amplified if you push with a larger force, or if you push from a greater distance from the hinge. So if you push right up against the hinge, it's harder to open the door. If you open it from further away from the hinge, it becomes much easier to open the door. And so it's this combination of a larger force or a greater distance, from the hinge. So this tells us that this idea of torque varies as you vary the force and as you vary that distance. That's going to give us the formula that we're going to use for torque. That's the symbol for torque, a fancy T. Torque is a vector, has a force and a magnitude and a direction. And it is equal to the force times, actually I shouldn't put that in, it's a cross product. The distance to the hinge. Now this is not a mathematical expression that we know how to deal with. That's okay. Instead we're going to use this guy here. Torque is equal to F perpendicular times R, the distance. We've also got this guy here, force perpendicular, so I want the magnitude, that force times R sine theta. So there's a couple different formulations here where theta is an angle between F and R. So there's a couple different formulations here. These will make more sense to you as you go off in university. This guy here is the one that we're going to try and use the most. I'll show you where some of this comes from. If we go up here, I'm going to redraw the door. Let's say that you're pushing on the door with a force that looks like this. Okay, so you're not pushing directly on the door, you're pushing angled on the door. When we say a perpendicular, F perpendicular times R, this distance here from the hinge to wherever the force is acting, that distance is R. And when I say F perpendicular, what I want is the component of that force that is perpendicular to the door. Well, if I look at what's going on here, I've got, there's an angle between my force and the thing that I'm pushing. If I call that angle theta, and I continue, or I complete rather, my component triangle, this angle here is also going to be theta, and so this is going to be my parallel force to the door. Oh, that's a theta there. So if I look at what's happening here, if I want to find the torque, if torque is equal to F perpendicular R, well, this is the same thing as my main force F. F perpendicular is F sine theta times my distance, which is where we get this expression down here. I want, actually, I shouldn't say F perpendicular sine theta. That should have just been F sine theta. My bad, guys, here. Sorry, let me fix that. Torque is equal to F R sine theta. The magnitude of the force times the magnitude of the distance times the sine of the angle between them. Where theta is just the angle between F and R, because if we look at how this triangle or the alternate interior angles work, that angle there is going to be the same as that angle there, which allows us to find F perpendicular. As you go off and, like I said, study this in university, there's going to be other mathematical tools that you're going to use, namely cross product, but we're not going to get into, we're not going to use that there. I just wanted to introduce to you it so that you can see it, but we're not going to use it this year. Units of torque. If we look at what's happening with torque, torque is a force times a distance. So that's going to be a Newton times a meter. So torque is measured in Newton meters. If torque is a rotation, then it could, the two directions for a rotation are either this way or this way around some point. So this is going to be counterclockwise, and this guy here is going to be clockwise. Typically, we assume a clockwise rotation to be positive and a counterclockwise rotation to be negative. If the force acts at the pivot point, that means R is equal to 0. So if it acts at the pivot point, R equals 0. That means the torque equals 0. There is no spinning if you push on the hinge, push on the door. If there are several torques acting on an object, then the net torque is the sum of those torques. Torque net equals torque 1 plus torque 2 plus ... Torque N, which is, you can write it like this. You guys saw this last year too. The sum of all your torques. Okay? This is the idea of torque. So flip the page. Let's do an example. Classic example of torque is the seesaw. So consider the seesaw. The seesaw is a 10 kilogram beam pivoted at the middle. We want to draw all the forces acting on the beam, and we want to find the torque, the net torque, and the direction. So the magnitude and the direction of the torque on the beam. So the pivot. Pivot's right here. I'm going to draw the pivot a little bit more definitively. So there's a pivot acting there. It's acting at the middle of the beam, which on a uniform beam also happens to be where we draw gravity acting. So gravity is acting right at the pivot. So we've got FG there. And the pivot is the place that the seesaw is sitting on. So that's a surface there. So we're going to actually have an FN upwards here. Now, both of these guys are acting at the pivot point first, so neither of them are going to contribute to the torques. Relatively straightforward. FG here is that's a 10 kilogram beam, so that's 98 newtons. We don't know what FN is yet because there's other forces acting downwards. We have a 10 kilogram person and a 5 kilogram person there. So they each have an FG downwards. This FG is going to be 98 newtons. This FG is going to be 49 newtons. And those are all the forces acting on this beam. So Fn is the only force acting upwards, so it has to balance out all three of these forces acting downwards because, as we saw in the previous lesson, this thing is in equilibrium up and down. The whole seesaw is not flinging up into the air or crashing down into the ground. So my Fn then has to be equal to my Fg's all added together, all my downward forces added together. That's going to be 245 newtons. So those are all the forces acting on our seesaw. Now if I take a look at what's happening here, I've got a force of gravity acting 2 meters from the pivot, and this force here, if I imagine what's happening here at the pivot, this thing is going to cause this guy to drop this way. Okay, so he's going to cause a swing this way, and this guy is going to cause a swing this way. If I imagine this is not here, I put the pivot there, the seesaw is going to drop like that. Okay, so both of these forces are providing a torque, or applying a torque, to my seesaw. Now this torque, just like we had F net equals ma, we're going to set up torque equals F perpendicular r. F perpendicular r. My force is 90, and it is perpendicular because it's straight down and my seesaw is horizontal. So that's 98 times the distance to the pivot is 2 meters. So my torque is 196 Newton meters, and this way is counterclockwise. There's my direction. This torque is equal to the force perpendicular times the distance to the pivot. Well, that's going to be 49 times 1.2, which is going to equal 58.8 Newton meters clockwise. So look at what's happening here. I've got 196 Newton meter counterclockwise torque, and I've got a 58.8 Newton meter clockwise torque. Well, these are going to act in opposite directions. We have to say now not just which way left and right or up and down is positive. We have to talk about which way rotationally we want to be positive and negative. Typically, clockwise is positive. So when I want to find the net torque, let's call that torque 1, let's call that torque 2. That's 1, that's 2, so this is person 1, this is person 2. So my torque net is going to be torque 1 plus torque 2. Well, torque 1, if clockwise is positive, this is going to be negative. This is going to be negative 196 plus 58.8. So that tells us that the torque is negative 137.2 Newton meters. Well, if it's a negative torque and we said clockwise was positive, then counterclockwise is going to be our direction here. So it's going to be 137.2 Newton meters counterclockwise. I don't have to have negative and counterclockwise. It's one or the other. Okay. Relatively straightforward. It's going to get more complicated. Flip the page. Now, if the pivot is not located at the center of an object, then the weight of the object itself is going to cause the object to spin. Gravity, the attraction from the Earth, acts on every bit of the meter stick. It's acting everywhere downwards, even on this end here. But summing this up would require mathematical skills most of us don't have yet. Basically, we'd have to take the integral, the sum, over the entirety of the object. But to make our lives a little bit easier, what we can look at is how gravity acts at the center of mass. We can take gravity to act, on average, at the single point at the center of mass. For a uniform object, center of mass, which I know it says that in the next sentence, but write it down anyway. In a uniform object, an object that is the same throughout, the center of mass is located at the center of the object. So, if this is a 2 meter long object and it's uniform, the center of mass will be 1 meter in, and Fg will act down at that point. And we'll have a pivot, and away we go. So, let's look at this example. I want to find the net torque for an object that looks like this. This could be a crane. I don't know. Let's say it is a crane. Okay, so there's my structure. That's where this thing is going to pivot from. I've got a 1 meter distance from here to here. We're told that this thing is 5 meters long. This is 5 meters. This distance is 1 meter. The center, this distance here, is half of 5, so it's going to be 2.5 meters. Which means this distance here is going to be 1.5 meters. We need the distance to this from the center, or from one of the ends to the center, and then we need the distance from the pivot to the center of mass, because this is where gravity is going to act there. So I've got Fg from the beam, and I've got Fg from this hanging object here. This Fg we're told is 20 newtons. It says it right there. This thing weighs 8 kilograms, so Fg is going to be 8 times 9.8, which is 78.4 newtons. Typically, clockwise is positive, so let's put my positive direction in there. This guy is going to create a torque that goes this way. This guy is going to create a torque that goes this way. I mean, you can imagine it. Put your finger at the pivot and use your pencil. This force downwards is going to do this, causing the object to rotate. This force here is going to cause the object to go spin. It's important to whistle. So let's use our torque equations to figure out what the net torque actually is. Here, I'm going to have torque equals F perpendicular times the distance to my pivot. Well, that's just going to be 20 times 1, which is a torque of 20 Newton meters counterclockwise. And this guy here is going to have a torque of F perpendicular R equals 78.4 is my F perpendicular. Now the distance to my pivot is 1.5. So that's going to be 117.6 Newton meters. And he's going to be clockwise. So my net torque is going to be, clockwise is positive, so that's 117.6 minus, because it's counterclockwise, it's negative 20, equals 97.6 Newton meters. And because this is positive, my direction is going to be clockwise. And there, we're done. Okay, flip the page again. We're going to do one more example. Flip the page here. This is the argument that I gave you on the front page. What if the force is not perpendicular to the object? Then we need, once again, to consider components. If the in the diagram below, so here's a door, we can see it that it is the component of the force that is perpendicular to the object that makes this thing spin. Parallel component would just pull on the pivot. Okay. So I've got F perpendicular, which I could draw on my component triangle right here. There's my F parallel. Now it's important to recognize that it actually acts where the force acts, but in my component triangle it gets drawn kind of oddly like this. This is going to be F sine theta, so my force perpendicular is going to be force times the sine of the angle theta between the object and the way the force is acting, between R and the way the force is acting. So we can modify the torque equation. I wrote it already. Torque F perpendicular R is the same thing as my force times the distance from the pivot and the sine of the angle between them, which I've already kind of given you. Let's do another example that requires exactly that. So I've got a beam acting off on an angle. Let's look at what we've got here. Let's label all of our forces. We've got tension in the rope. Okay, that's one force. We also have Fg acting straight down from the center of mass. I've got an Fn, because this is where it's resting on the surface. But Fn is where the pivot is, so it's not going to create a torque. Causes no torque, because it's acting at the pivot. This is our pivot point. Sometimes it's helpful just to draw that in more explicitly. And I'm going to say that this direction here, clockwise, is positive. So those are the forces that are acting. Now let's fill in some more information. We know that Fg, we're told that the beam has a mass of 5 kilograms. So this Fg is going to be 5 times 9.8, so that's going to be 49 newtons. We're told that the torque in the rope, the tension in the rope, force of tension, is going to equal 25 newtons. And we want to find the net torque on our object. Now, here's what we're going to have to do. I've got that guy there, and I've got this guy here. These are the perpendicular components. So this is going to be Fg perpendicular, and this is going to be Ft perpendicular. Now this should be longer. It should go out into the question here. But these are the guys that are actually going to be causing the torques. Now we can use this. We can use the components. We can use F perpendicular R. We can figure out what Ft perpendicular is and what Fg perpendicular is, or we can go straight to this equation here. Okay. I'll show you what this is going to end up looking like. Now, the torque from gravity, so let's label them just like we would label forces. I've called it torque G, but whatever, is going to equal Fr sine theta. Now, if we look at this thing here, this forms a 90-degree angle because that's acting straight down. This is 35, so this angle right here between Fg and the beam is 55 degrees. So this is going to equal my force, which is 49 newtons, times the distance to the pivot. Now, Fg acts in the middle of the beam, and we're told that this beam is 8 meters long. So this distance here is 4 meters. So my R is going to be 4. And now the angle between the force and the beam is 55 degrees. So it's going to be sine 55. So my torque then is going to be 160.55 Newton meters clockwise. Relatively straightforward. This guy here, again, we could break this thing up using components. If that's 40 degrees, then that's 50 degrees and blah, 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 blah. Or we could just set this thing up and say, okay, well, the torque from tension is going to equal to my force, which is 25 newtons, times the times the distance to the pivot. Now we're told that this is half a meter. So then this whole thing, how will I draw it? I'll draw it in red here. This distance, if that's half a meter and this is an 8-meter beam, that's going to be 7.5 meters. So my tension is going to be 25, my force, times 7.5, the distance to the pivot, times the sine of the angle between my force and the object. And so in this case, that's this 40 degrees here. The sine of 40. So then my tension is going to be 120.52 Newton meters. Which way? Well, this is pulling the beam up this way, so that's going to be counterclockwise. So then my net torque is going to be, if I said clockwise with positive, it's going to be 160.55 minus, because that's counterclockwise, that's negative, 120.52 is going to give me a net torque of 40.03 Newton meters. It's positive, so that's clockwise. Oh, sorry. And we're done. Okay. If we wanted to, we could have found these components, but it ultimately, I mean, the power of the torque equation is that we don't have to break it up that way. Now, there is an alternative way to find torques. If we look at this here, there's another way to determine torques in cases that are gross. I am not going to go through this with you guys because I'm just going to rig it so you don't have to deal with problems that look like this for the sake of time, really. You will have an opportunity to look at problems like this when you revisit Torque Again at university, and you're not going to lose anything by me not addressing it. So there's some more stuff in here. We're going to skip it for the time being. And it's really no loss to you guys, but for the sake of time, yeah, I'm not going to cover that. So flip the page. The homework that I'm assigning for this chunk is the following. I want you guys to do questions 1 to 3 here. And I want you to do, so 1, 2, and 3, do those all. And I want you to do 5. And I want you to do 7. Yes, 7 is the only other one. There you go. As always, so this stuff is very new. I know that this is not reviewing something. So work it through. You've got to spend the time to work on these problems. Otherwise, it's not going to make sense, and the questions are just going to get more complicated. So if you've got questions, please do come see me. Best of luck to you.